Welcome to the second in a series of videos on the step response of second-order systems. I talked about underdamped second-order systems. They are the ones that can oscillate. A first-order system can oscillate. An overdamped second-order system does not oscillate. And a critically damped second-order system does not oscillate. So underdamped second-order systems are the ones that oscillate. And those systems are the ones where zeta is between 0 and 1. Now I talked about that there were three characteristics for a second order system. I think I have that was probably above here. K, omega n, and zeta. And they determine how the system is going to behave. As I described in the last video, K actually determines this vertical jump when a step response is fed in. How much it jumps depends upon K. So the vertical part of the jump is solely dependent upon K. Now the other two parameters, omega n and zeta, are tied in with each other, and like I said in the last video, the frequency that we're seeing here is not the natural frequency of the system. This system has damping. You can tell it because the oscillations die off, and what causes those oscillations to die off is the damping of the system. The more damping, the quicker they'll die off. So the relationship between the natural frequency and the damped natural frequency depends not only on omega n, which is the natural frequency of the system, it also depends upon zeta. So we have this, the frequency that we see is the damped natural frequency, and it depends upon zeta and omega n. Now there's another interesting and important feature of this step response, and that's called overshoot. That is, so we go from a certain point before we introduce the step input to a new point when the oscillations die off. And what the overshoot is the overshoot is the percentage that the response jumps up over the eventual new level that the system will arrive at. That's called the percent overshoot. This is actually the overshoot. So if we start at 3, because that's our eventual steady state level that we're going to be at, we are up here at 4.5, a little bit higher. So actually that's 1.5 up and a little bit more above our final state here at 3. So we have greater than 50% overshoot here. Now the nice thing about overshoot from trying to identify the system and identify the amount of damping it has in it is that the percent overshoot depends solely upon zeta. It does not depend upon omega n. The problem with the damped natural frequency is it depends upon omega n and zeta, but the overshoot only depends on zeta. And what that means is that you can, if you have a system that's unknown and you put a step response into it and you get a wiggle like this, you can say, oh, it's got like a little over 50% overshoot. Well, I can figure out from that what the zeta is. And here's the relationship right here between percent overshoot and zeta. Notice that on the right hand side, so the percent overshoot is something that we can measure from our graph. We get our graph by connecting an oscilloscope or some type of data logging system to our system so that we can record this response, and we can look up there and actually measure what the percent overshoot is going to be. The percent overshoot is just the overshoot divided by the distance up to the final steady state. And once we have the percent overshoot, And so that's how you do it. Here's our relationship between percent overshoot and zeta, but this doesn't help us if we're measuring percent overshoot and we're trying to find zeta. But we can invert this relationship, and if we do, and this is the useful relationship here, you can put in your percent overshoot here. Actually, you put it in as a number between 0 and 1. So this is a little bit complicated formula, but as you can see, the only thing over here is the percent overshoot that we don't know. And we can put this in here and then actually calculate what zeta is. Now, once we have zeta, we can actually go back and get our omega d. We find the period of our damped response. And from the period, you can figure out omega d. So if you've used the overshoot to figure out zeta using this equation, and then you can measure omega d by finding the damped period and then converting it into a damped frequency, knowing zeta and knowing omega d, you can solve for omega n. So again, how this would work out in real life is you have a system and you don't have any idea what its dynamic properties are. You put a known step into that system. From how much it jumps, you can figure out K. How much overshoot it has, you can figure out zeta. Knowing zeta, you can then get the damped frequency, or damped period, and then get the damped frequency from that. And from the damped frequency and zeta, you can figure out what omega n is. So what will happen if you do that is you know then the three performance parameters that make up a second order system. You know K by how much it jumped, you know zeta from the percent overshoot, and you know omega n because you knew the damped period and the damped frequency, and you can figure out omega n from that. So you can get the performance parameter version of the second order step response. Now, I haven't really defined this yet, and I should. K, zeta, and omega n are called performance parameters because they look at the way the system performs when you put a step input into it, and then from that you can get your transfer function. You also have physical parameters in a system, and what will happen is, like for instance, an MCK system, which you can find a video in this control series about. It has three physical parameters: the mass that's vibrating, the damping, and then which is C, and then K, the stiffness of the spring in the system. Those are physical parameters, and from them you can actually come up with the performance parameters, K, zeta, and omega n. The performance parameters are related to this curve here, this response curve, and that's why they call performance parameters as opposed to physical parameters. Now, if we look at our system response and our system transfer function, this is the transfer function if you know K, zeta, and omega n. And there are actually two versions of this. You can use this version here, but if you divide the top and the bottom by omega n, you have this version over here on the right. And the good thing about the version on the right is that you have a 1 right here in the denominator, the constant term. You need that for a certain reason, and we'll talk about that later in another video. Notice that the first order system that we were looking at before has a 1 as the constant term in its denominator also. So that's important. And actually, I'll tell you the reason that this is important, or at least the characteristic that is important here. If there's a 1 here, and only if there's a 1 here in this constant term, then whatever is in the numerator is going to be the gain of the system, the steady state gain of the system. If you don't have a 1 here, then whatever's in the numerator is not the steady state gain of the system. In fact, what's the steady state gain of the system is whatever's in the numerator divided by this constant term here. So it's often convenient to manipulate your denominator of your transfer function, which is what I did here in this case. I had omega n squared here, and I divide the top and the bottom by omega n squared, and that leaves a k on top, and of course a 1 here in the constant term in the polynomial in the denominator. Now, I'll stop here and start a new video because I want to talk about some other important parameters that are related to the response of the system.